In this video, we will look at Millikan's remarkable oil drop experiment that enabled him to measure the charge on an electron, effectively the elementary unit of charge, which, as we will see, is an incredibly small quantity in terms of coulombs. So Robert Millikan in 1911 worked on this experiment, and in fact later on got the Nobel Prize in 1923 for measurement of the elementary electric charge. That's what we'll be looking at today, along with his work on the photoelectric effect. And of course, we know that Einstein also received a Nobel Prize related to the photoelectric effect as well. But let's press on with the oil drop experiment that Millikan worked on. And basically what we've got here is a glass chamber. And here we have a schematic of that showing more clearly what is going on. So let's zoom in to take a closer look. So that's the glass chamber, and what happens is that oil droplets are sprayed in, so there's a very fine mist of oil, and the oil droplets here are in fact charged by ionization of the air. So X-rays can be used to ionize the air, and effectively a number of electrons, 1, 2, 3 or more electrons, can attach to these oil drops, this very fine mist of oil. And what happens is that some of these oil drops will descend inside this glass chamber into this lower part here, which is effectively a capacitor. It's a positive and negatively charged pair of plates, and there's air in here still as well. And you can see here there are electric field lines going from the positive anode to the negative cathode. This is a uniform electric field. And then we observe one or more oil drops that fall through this hole from that mist above with a charge attached, of course, and they fall through the hole and will be pulled down, of course, due to gravity. But then we're also able to use this electric field to cause the negatively charged oil drops to actually rise upwards towards the positive anode. So let's take a look at how this experiment can be used to find the fundamental unit of charge. Okay, let's take a look at what would happen then if we did take a look with a microscope to examine those oil drops that have fallen through that gap. This video will show that. Here we're showing an oil drop being accelerated upwards because it's got negative charge as it's got electrons attached to it. There we can see it's being accelerated upwards, and then when the electric field is removed, the oil drop will be in free fall. So let's take another look. This is an oil drop going upwards, and then as we release the electric field, switch it off, then we get it back into free fall. There it is, being attracted towards the positive anode. And again, if the electric field were to be released, when we release the electric field, so the oil drop will be in free fall and ultimately reach some terminal velocity. And we'll be relying on that in order to measure the fundamental unit of charge. Okay, so let's move on to the next slide. This is another schematic now where we're just looking at the capacitor plates there. These are oil droplets and we're just looking at one of them. And so here we're depicting the fact that we're looking at the space between those two electrodes, making up that capacitor with air in the middle here. And of course, we've got the fact that an oil drop will be pulled down due to gravity. And so the weight, the force acting downwards due to gravity, the weight is equal to mass times acceleration. And so that's just Newton's second law, where the acceleration is due to gravity. So that's typically about 9.8 meters per second squared. So this is just the downward force due to gravity acting on one of the oil drops. And then what we can do is rewrite that expression by considering, well, how could we rewrite the mass in terms of the radius of the oil droplet? So 4/3 pi r cubed would correspond to the volume of a sphere. So that's the model of the oil droplet. We're imagining it is exactly as a sphere. And then, of course, if we're using the volume rather than the mass, then we've also got to include the density, because density is equal to mass over volume. So imagine rho is equal to mass divided by volume, and therefore mass is equal to density times volume. So that's what we've got there, just as a substitution. Let me just clarify that substitution. And so this is the density. And you'll notice that we've got a correction here for the density. So rho is the density of the oil droplet, and then we're subtracting off the density of the air. So that's a necessary correction to give the effective density of the oil droplet. And a good way of understanding that is to say, well, what if the oil droplet were instead just like a sphere of air? Then we'd have rho air minus rho air, which is effectively 0. And so therefore we would not expect a kind of a drifting downwards if that sphere is of the same density as its surrounding medium. So that's why we've got this correction here. We're interested in the relative density of this oil droplet compared to the surrounding air, hence that difference there. Okay, now as mentioned, due to the ionization of the air in that section above in the glass chamber, this oil droplet will have negative charge attached to it. And so there's some net charge Q, capital Q. It could be one or more electrons. We don't know that at the moment. So what we can do then is consider the charge Q on that droplet, and then remember, of course, that we're applying an electric field. Okay, this is the positive anode, the negative cathode, and we're applying an electric field due to a potential difference. And so therefore the force acting on that oil droplet, which has a charge of Q, this is just a well-known equation, force due to electric field on a charged particle of mass Q, charged particle of charge Q, the force acting on it is just the charge times the electric field strength. Okay, so, and then if we rewrite that, we can say, well, the electric field is in volts per meter, and so we can look at the voltage applied here over the distance d. So QV over d is the force upwards attracting that negatively charged oil droplet towards the positive anode. Okay, so what we're going to do is balance those two forces, because what we'd be able to do is when an oil droplet is falling between the two plates, we can actually adjust the electric field such that the gravitational force downwards, the weight, matches the electric field attracting the oil droplet upwards. And so if we adjust the electric field E, in other words the potential V, we could hopefully get the oil drop to remain stationary, and then we'd have this crucial equation here that would hold true, which is the force upwards, Fe, which is QV over d, would need to equal the gravitational force downwards, the volume times the effective density times the acceleration due to gravity. Okay, that's just equating those two forces. And then in principle, we're all good to go. We could solve for the unknown charge Q on that oil droplet. However, in this equation, we don't yet know the radius of the oil droplet. Okay, so this is what we're going to solve next. And just before I show you the solution to finding the radius, we need to quickly look at what's known as Stokes Law, which gives us the drag force when a sphere is falling through, or rather moving through, a viscous fluid. So we're assuming the air to be like a viscous fluid, and the oil droplet, of course, is given by this sphere. So I'm not going to derive this equation, but you can look it up for yourselves. Effectively then, if we've got some downward force here, imagine it's being pulled down due to gravity, that's the weight that we showed in the previous slide, then that will be matched by this drag force as the sphere moves downwards through this viscous fluid, and that drag force is just 6 times pi times the radius of the spherical object times the dynamic viscosity of this surrounding fluid, and then also crucially related to the velocity, the speed of that sphere. So hopefully this makes sense. In other words, the faster this sphere is moving, the greater the drag force. The larger the radius of this, the greater the drag force. And of course, the greater the viscosity of the fluid, the greater the drag force. So hopefully this equation makes sense, because we're going to use that next to help us find the radius of the droplet, and therefore to go back to that original equation and find also the charge on the oil droplet. Okay, so this is where we were then. We've got an oil droplet that if we don't apply an electric field, it will just be moving downwards. And so that's what we're going to do here first of all. Then we're going to switch off that electric field. and we're going to allow that oil drop to fall downwards and reach some terminal velocity. So imagine the case of skydiving, where someone will jump out of a plane and then be in free fall, and of course they're going to use a parachute and so on, but they will reach a terminal velocity when they will no longer be accelerating. They'll reach some terminal velocity. And so likewise, this oil droplet initially will be accelerating downwards, and then it will hit a final terminal velocity whereby the velocity is constant. And what we can do, if you remember that video before that I showed of the oil droplet moving up and down, we can look at the gradations on that through the microscope to see the distance traveled by the oil droplet within some amount of time, of course, that we can measure. So we can measure distance, we can measure time, and therefore we can calculate the terminal velocity of an oil droplet. And that then is crucial for plugging in to this expression here, which says that if this is now in free fall moving downwards at a terminal velocity, then we can find out what the equal and opposite drag force must be. Remember, by Newton's first law, if we've got constant velocity, there is no net force. And so in this case, if this is just moving down at constant terminal velocity, there's no net force, which means the drag force must be matching the gravitational force downwards. Okay, so let's plug that expression in. So we can balance, therefore, the weight with that drag force as mentioned. So we just equate this with what we've previously looked at. So this is effectively another force balance. The first force balance that we're going to revisit in a moment was between the electric field and the downwards force, where we're suspending the oil droplet. Now we're looking at the drag force and equating that with the downward weight when the oil droplet is in free fall. Okay, so let's solve this force balance, and the reason we're going to manipulate this equation, of course, is that we're trying to find the radius of the oil droplet. So we can just do basic algebraic manipulations here and solve it for, here at the moment we've solved it for r squared. And of course, let me just go back there. If we can solve this for r squared, then of course we can solve just by taking the square root to get the value r, the radius of the oil droplet. Then, if we've got the radius of the oil droplet, we can return back to our previous force balance, where now we have the case of suspending that oil droplet so that it's not moving, where we've got the force upwards due to the electric field, equal and opposite matching the downward gravitational force, the weight. Okay, so now we're back to QV over D, in other words, charge times electric field, volts per meter, is now equated also to the weight of that oil droplet expressed in terms of the density of the oil, which is easy to measure, and likewise now expressed in terms of the radius, which we've also just found a way of measuring. So we can measure the radius, and therefore we can put the radius into this equation and solve for capital Q, which is the charge of the oil droplet. Okay, so now, as mentioned, then we know all the terms in there, and therefore we can solve for Q. And as I indicate here, and we'll see in a moment, all the measured values for Q can all be found to be effectively integer multiples of some fundamental unit. So let me show you the results here. Here are the measured radii of various oil drops. In other words, this experiment can be done many, many times. You can see it's been done dozens of times in this example here. So we've got all these various values for the radius that's been measured of each individual oil drop experiment, where one of those oil drops has fallen through between those capacitor electrode plates. And so we've measured the radius, equating the weight with the drag force from Stokes Law. That's how we found the radius. And then once we found the radius, we've then been able to calculate the charge capital Q on the oil droplet. And what you'll observe here then is the measurements of the radius seem to be fairly evenly distributed across this x-axis. This is in 10 to the minus 7 here. So these are quite small oil droplets. But you'll notice that capital Q, the measured charge, you can see it takes on these very distinct values. In other words, there are no values of capital Q in that range there, none in that range there, none there, none there. In other words, it's always basically in these integer multiples of this fundamental unit, which is about 1.6 times 10 to the minus 19, which of course is the fundamental unit of charge. This would correspond then to either having 1, 2, 3, 4, or 5, and so on, electrons attached to that oil droplet. So this is a very remarkable result. By measuring the radii of various oil droplets, measuring the charge of those various oil droplets, we reveal this fundamental spacing in the charge, which is the fundamental unit of electric charge. And what Millikan found was this value here, which compares very well indeed with the modern value for the electric charge, rather the charge on an electron, which is 1.6022 times 10 to the minus 19. Millikan was very close there. And you can see that over time, the value has been improving, and we now arrive at that final modern value. So I hope that's been of use to you to understand how Millikan won a Nobel Prize for this remarkable experiment measuring the fundamental unit of charge. Thanks very much for listening.